IPv6 can look intimidating at first, but if you're studying for the CCNA, it's one of those topics that gets much easier once you break the address into simple pieces. The reason it matters is simple. IPv4 ran short on address space while the number of internet-connected devices kept exploding. IPv6 was designed to solve that scale problem and to support modern networking more cleanly. In this video, you'll learn how IPv6 addresses are built, how to read them, and how to recognize the parts that matter on the exam. At its core, an IPv6 address is a 128-bit logical address used to identify an interface on a network. Instead of IPv4's 32 bits written in dotted decimal, IPv6 is much longer and uses hexadecimal notation. A full IPv6 address has 8 groups, and each group is separated by a colon rather than a dot. So when you see something like 2001:0db8:0000 and so on, you're looking at 8 blocks lined up in order. That format may look busy, but it follows a very regular pattern. And that pattern is what makes IPv6 learnable. To read IPv6 comfortably, you only need a small amount of hexadecimal. Hex uses the symbols 0 through 9, then A through F. After 9, the values continue as A for 10, B for 11, all the way to F for 15. The helpful shortcut is that one hex digit always represents exactly 4 bits. That means 4 binary bits can be compressed into one cleaner hex symbol, which makes a 128-bit address far easier to write and read. For example, binary 1111 becomes F, and 1010 becomes A. You do not need advanced math here. You just need to get comfortable translating the symbols and spotting the structure. Now let's break the address into its building blocks. Each of the 8 groups is called a hextet. Each hextet contains 16 bits because it is made of 4 hex characters, and each hex character represents 4 bits. When you put all 8 hextets together, you get the full 128-bit IPv6 address. Just like IPv4 uses a network portion and a host portion, IPv6 also divides the address into meaningful sections. In many CCNA examples, the first 64 bits are the network prefix, and the last 64 bits identify the interface. That's why you'll constantly see /64. It is the standard subnet size in most modern IPv6 networks. You should think of /64 as the normal starting point, unless the question gives you a different prefix length on purpose. One reason IPv6 gets easier fast is that we usually do not write every address in its full expanded form. The first shorthand rule is to remove leading zeros inside any hextet. So 0db8 becomes db8, and 000A becomes A. But a 0 at the end stays if it is needed. The second shorthand rule is to compress consecutive hextets that are all zeros by replacing that run with a double colon. For example, the IPv6 address on your screen can be shrinked to 2001:db8:1. But there is one rule you must not forget. The double colon can be used only once in a single address. If you used it twice, the missing 0 blocks would become ambiguous, and the address could not be expanded correctly. On the CCNA, practice expanding and compressing addresses until the pattern feels automatic. Now let's look at the main IPv6 address types you need to recognize quickly on the exam. Global unicast addresses are the public-style addresses used for normal routable communication on IPv6 networks. They commonly begin in the 2000:3 range, which is a good exam clue. Link local addresses begin with FE80:10 and are used for communication on the local link. Unique local addresses are like private style addressing in IPv6. They usually start with FC or FD, with FD often shown in examples. Multicast addresses start with FF, and IPv6 uses multicast heavily instead of broadcast. Anycast is a concept where the same address can exist on multiple devices, and traffic goes to the nearest one by routing. Also remember the special addresses. $:1 is loopback, and plain $: means unspecified. Link local addresses deserve special attention because they are central to how IPv6 actually operates. Every IPv6 enabled interface can create a link local address automatically, and those addresses live in the FE80:10 range. A link local address works only on the local network segment. Routers do not forward it across the wider network. That still makes it extremely important because devices use link local addressing for neighbor discovery and local communication. In IPv6, a host can talk to nearby devices and even reach its default gateway using link local addresses. So even if a device does not yet have a global unicast address, it can still do useful local IPv6 communication. For the CCNA, remember this as a big idea. Link local is not optional background detail. It is part of normal IPv6 operation. IPv6 subnetting feels different from IPv4 subnetting, and that difference actually makes life easier. In IPv4, we often spend time squeezing the right number of hosts into a small subnet. In IPv6, the focus is usually on prefix planning. You are carving out clean network prefixes, not worrying about running out of host addresses inside a /64. Prefix length tells you how many bits belong to the network portion, just like CIDR notation in IPv4. You'll also hear about nibble boundaries. A nibble is 4 bits, which matches 1 hex character. That is why prefix lengths like /48, /52, /56, and /64 are easier to work with. They line up neatly with hex digits. When a prefix cuts cleanly at a nibble boundary, reading and allocating subnets becomes much less error-prone. So for CCNA subnetting questions, think in terms of structured prefix blocks and readable boundaries, not tiny host math. Once you understand the address itself, the next question is how a device gets that IPv6 address. The most direct method is static assignment, where an administrator manually configures the address and prefix length. Another common method is SLAC, which stands for Stateless Address Auto-Configuration. With SLAC, a host can learn network information from router advertisements and build its own address automatically. DHCPv6 is the third big method. It can provide addressing details and other configuration information in a more managed way. For CCNA study, keep the big picture in mind. Static is manual, SLAC is self-configuration, and DHCPv6 adds centralized control. Before we wrap up, there are a few related IPv6 ideas that connect directly to addressing and show up often in study materials. First, IPv6 does not use ARP the way IPv4 does. Neighbor discovery takes over that job. Second, IPv6 does not use broadcast. Instead, it relies on multicast to reach groups of interested devices. That is why multicast addresses matter more in IPv6 than many beginners expect. And throughout all of this, prefix notation is essential because it tells you where the network portion ends. If you can read the prefix, recognize the address type, and apply shorthand rules, you're already building real IPv6 fluency. So the big takeaways are these. IPv6 uses 128 bits. It is written in hexadecimal, and most CCNA examples revolve around reading structure and prefix length correctly. Remember the essentials: /64 is common, shorthand removes zeros cleanly, and prefixes like 2000, FE80, FF, and :1 should jump out at you. Keep practicing by expanding and compressing real IPv6 addresses out loud. The more patterns you see, the more natural they become. If this helped, keep going with more CCNA networking topics, and give yourself a few practice questions right after this video while it's still fresh. You've got this.